So, circle theorems, all right? The first thing we need to go through is the actual sort of vocabulary of circles, all right?
Yeah.
So, let's... Cool. Standard circle, we know that the edge is circumference,
Yeah.
and across the middle, that's the full diameter, that's your center there. So
Yeah.
that is the diameter going that way, and half the diameter is your radius, all right?
Yeah.
I know it's basic, but it's good to just have everything in one place. Then from there, okay, that is called a what? Do you remember?
The sector.
Well done. Okay. And if I then slice it like that, what's this bit here?
Is that a segment?
It is. Excellent. Okay. And then there's two other bits we need to know. Given any 2 points, let's take that point there and that point there, all right? We have a piece of the circumference, like that.
Yeah.
What's that called?
This one I was thinking about. I forgot this one.
No problem. Minor arc,
Oh, yeah.
all right? Now, the minor arc is the shortest piece of circumference between 2 points, or shorter, if you like, okay?
Yeah.
And the other way around, if you were to go the long way round, that would be the major arc.
Yeah.
All right. So those are effectively all the bits of a circle that you need to know. All right. Couple of special things to note is that when you have a segment, defined by 2 different points on the circumference, then the sides, right, these two, so that one there and that one there, are equal because they're both radii. That's a radius and that's a radius. Yeah? So whenever you create a triangle like that, at the very least, it's going to be an isosceles triangle because it's got 2 equal sides. Right? So that's a useful property to remember. Okay?
Yeah.
Any questions? Anything on that?
No.
No? All right, cool. So let's move on from there and go through the actual theorems one by one. So, first one, I'm cheating a little because this one tidies up the shape. Okay, so if you have a diameter, right, and from the diameter, if you join the triangle, create a triangle to the circumference like that, okay, that angle there will always be a right angle.
Okay.
Okay, so if this is through the center and it's a diameter, doesn't matter where you join it. Okay, so I could put it there and there, right? That would also be a right angle. So anywhere along the circumference, that side or this side, that's always going to be a right angle at the circumference. Okay?
Yeah.
And writing it out, so what we call this, right, that angle there, right, is effectively sort of held up, if you like. Let me just do a little thought for you there. So this angle, right, is held up, or it covers this length here, doesn't it? Yeah? Do you get my point? Like an umbrella. All right. So what we say is that if that's A and that's B, then this angle x, x is subtended by. Does that make sense? So all it
X is,
means, yeah, so the x is basically sort of like held up by A and B. All right? So x covers that length there, A to B. All right? Same
yeah,
way, these right angles, whatever angle I create at the edge, all right, those angles are subtended by the diameter. So by that diameter from, I'm going to call that A and B, that point there and that point there. Does that make sense? Yeah. So the rule is angle subtended by diameter is 90 degrees. Okay. And that angle is at the circumference. So that's the first rule. Does that make sense?
yeah,
All right. And if this subtended thing is very important, it's going to come up over and over again. Right? We're going to use that word a lot. Okay.
yeah.
Any questions?
No, I don't think so.
No? All right. So, number two, and I'm going to try and run through this quickly now, otherwise, we'll bore you to death. Okay. The next one is that if I have 2 points on the circumference, like an arc like that, all right,
Yeah,
again, A, B, something like that, then whatever angle I have here, wherever I create an angle using those 2 points, A and B, all right, so like this, those angles will always be the same. Okay? So angles, and whenever we talk about angles like we did here, usually, not always, usually we're going to mean at the circumference. All right? So angles subtended by same points, like in this case, AB, all right? Or same arc. See how this arc is effectively underneath the angle. So if I'm
yeah,
looking at that bit, so that's the arc. So both these angles are effectively covering that arc there, right? Exactly
yeah,
the same way, like that. So angles subtended by the same arc or same 2 points are equal. All right?
yeah.
All right. Number three. I'm not doing this in any particular order. It's just as I think of them. Okay. Next one. Oh, that was a very wonky line. I'm actually better with a fountain pen than I am on a screen. Right. So when you have, again, the same arc, right? Same points, A and B
Yeah.
if you like, and we create an angle at the center and at the edge. So there's that one there. The rule is that the angle at the center is going to be double the angle at the edge. All right. So this angle here, if it's the same arc again, like that, if you join it at the center and you join it at the edge from the same 2 points, the relationship is that the angle at the center is double the angle at the edge. All right. So when it comes to doing a GCSE question, if you just write angle at center is twice the angle at the edge, that's sufficient. You don't have to explain anything more than that. All right. Any questions on that?
No.
No? All right. Cool. Number 4. Okay. Let's take a cyclic quadrilateral as another one. And a cyclic quadrilateral is effectively where, the 4 corners of the quadrilateral are all on the circumference of the same circle.
Yeah.
All 4 corners. What's the name for a corner? Here. Vertices.
Yeah.
Yeah? So a vertex is basically a corner, right? So cyclic quadrilateral is where all 4 corners, i.e. the vertices, are on circumference of same circle, as in the diagram, all right? The special relationship here is that if we call that one A and that angle B, all right, then, okay, A plus B equals 180. All right, the opposite angles of a cyclic quadrilateral will add up to 180. All right, does that make sense?
Yeah.
And similarly, if I had C and D there, so A plus B will be 180, write that out again, and C plus D also 180. Okay?
Yeah.
Right, number 5. This one is one that seems to catch people out sometimes. Okay, and almost a proper tangent. But this one is a tangent
Yeah.
to the circle. And if now I have a triangle in there, okay,
Yeah.
like that, all right, there's a very special relationship between this angle here, right, and the opposite side angle here. Okay, so that's A and that's A. They're the same. All right. Now, this one takes a little explaining First of all, I'll write out the name of it. Do you remember what that one's called, or that theorem?
Which
Begins with
one?
an A.
Uh,
Okay. Alternate segment. Okay. Alternate segment theorem. So if in a question, an exam question, you get that set up and you are using it in one, like where you have to work out the angle, right, and give your reasons, then if you just write alternate segment theorem, that's again sufficient, right? You don't need to prove it or anything unless they specifically ask you to prove it, which is a different thing altogether, all right? Right, so that's the case there. The other part of it is that if you're using that rule, then technically this one would be the same as this one, right? So call that B if you like, and that's B. Do you see how that works either side?
yeah.
Yeah? All right. Now, the really important thing is that, and I'm going to have to make sure I do this clearly. How do you work out which one, right? In an exam situation, you might get confused. You see how angle A, this one here, right? It's formed by this line. Let's call it, I'm going to call that A, B, and C, right? So line AB, okay, is creating the angle A, right, with the tangent. Does that make sense? Yeah? All right. So if it's line AB here creating that angle, then the two angles, i.e. that one there and that one there, are effectively sitting on that line AB, right? It's not those, it's the other one. So in other words, look at where A is. It's the angle that effectively is opposite to it, like that. Does that make sense?
Do you need to repeat it one more time?
Yeah. So that angle A
Yeah.
is created by line AB and the tangent. Yeah? So effectively, you've got that one there and that one there. Okay? And these two angles here, that one there and that one there, all right? Those two sit on that line AB. Okay? So you ignore those two, it's the other angle that's equal to the angle A.
Oh, yeah.
Does that now make sense?
Yeah.
All right? Exactly the same. If I talk about angle B, all right, you see how, if I use this now, hang on, I want to use some other color. Let me find a color. Okay. Right, so again, I've got that. Oh, I'm not sure if that color works too well, but you see how that is created by the line AC and the tangent.
Yeah.
Yeah? So this angle at C and the angle at A sit on that line AC, right? So we ignore it. And the one we're talking about, right, is this one, opposite one. Does that make any sense?
Yeah.
Let me give you a short example, just a quick example to help you with that one, because this is the one that I think a lot of people get confused by, all right? So if I have, and a tangent like that, all right? And I do, well, I don't know, let's make it really weird looking. Like that, yeah?
Yeah.
And I want this angle here, for example. Let's say I know this angle here, okay? A, B, C, right? Which one is going to be equal to that?
Would it be?
Done. So, whoopsies, what's that? So if that's A, which the angle at A, the angle at C, or the angle at B, which one's going to be the same as A?
Would it be B? No,
Yeah, go on.
I think it would be.
Yeah. See, look, that angle A is created by the line AC, yeah?
On the tangent.
Yeah, and so whatever angles are on that line, so this one and this one, you ignore them. It's not that.
Yeah.
It's the third one. Okay? So this is the same as A.
Yeah.
See how that diagram looks very different to the one that you usually get in the textbooks, which is the one above it, yeah? But they're the same. Does that make sense? Yeah, so even if it's lopsided, weird, a sliver of a triangle, the rule still applies. Okay?
Yeah.
Then I could easily apply the same thing again and see how this one, there's an angle there, right? Between CB and the tangent, right? And so for that one, the angle at C and the angle at B, I ignore those, all right? The one that's the same as that, let's call that B again, is this one. Does that help demonstrate?
Yeah.
Yeah? Makes sense?
Yeah.
All right. Okay, let's see. All right. A couple more. I'm doing just the main essential ones, and then we can cover other ones later if we need to. All right. Let's see. Oh, okay. Okay. If we have from the center of a circle there any chord, all right. So a chord is just straight across, right, cutting the circle. All right. If you take a radius and join it to the chord like that, right, then it will always cut it in exactly half. All right. So there's a chord. So a radius intersecting radius at right angles to chord will intersect at the midpoint of the chord. Yeah?
Yeah.
Does that make sense? And so we will call that, effectively, it's a perpendicular bisector. All right? Have I confused you with that?
I don't think so.
Okay, cool. Right. I'm just going to... Right, so the last rule that we're going to do on here is when you have two external tangents meeting, so let's draw that. Okay, and this is not going to be easy. Wait, pay attention. Right. Oh, that's terrible. Why does it do that?
No problem.
I'll stick with that. That'll do me. So, I don't know, effectively there. All right? So you've got two tangents on the outside. And tangents from the center will always, like a radius to the tangent, will always hit at 90 degrees.
Yeah.
All right, so that's your center. And if that's the case, then the length of the tangent to where the tangents meet at A, for example, right, that will be the same length as that. Okay, so if I have the points A, B, and C, so A is where the two tangents meet, intersect. B is one of the tangential points. C is another one. All right, where those two tangents effectively meet, the length from the point of contact, i.e. B to A and C to A, will be equal. Does that make sense? Yeah?
Yeah.
So AB equals AC. That's one rule. And if you draw a line from the center to the point of intersection A, then the angles will also be equal, like that. Okay? Does that make sense?
Yeah.
All right. Okay. That's basically all the important theorems that you need. All right. And the couple of things that we mentioned, which I haven't stated as a separate theorem in itself, right? You remember right at the beginning, I said that the two parts of the sector, right? The two lines of the sector are effectively equal, right? So the when you have that, let me just draw that actually. Like that. Then that is a radius and that is a radius. Okay? So you're okay with that, all right?
Yeah.
And we've done all of that. So yeah, I think we've covered all the bits that you need, all right? The last bit that I sort of hid under there, the chord rule, etc. So all of that. Any questions on what we've covered so far?
No, I don't think so.
No? All right then. Okay. I'll stop that there. I'll post that for you, and then let's give you some questions to practice on. We'll work through some questions together. All right?
All right.
Okay.